Hi there, in this video we're going to derive the inverse Laplace transform and we're going to have a wee look at it graphically. Now we'll take advantage of the fact that we can write the Laplace transform as a modified Fourier transform, so we can write a function f of t and we can modify it by e to the minus sigma t. Okay, so that's our modified function, and then we can find the Fourier transform of that function. Okay, so this whole thing here becomes our Laplace transform, and then what we want to do is find the inverse of this Laplace transform. So we find the inverse by finding the inverse Fourier transform of this. So this will tell us then that our inverse transform of sigma plus j omega is going to equal that there. Okay, so by doing that, we can now cancel out the forward transform, the inverse transform, so you're just left with an inverse transform of our sigma plus j omega, and that's going to equal our f of t e to the minus sigma t. Now we'll take the e to the minus sigma t over and we'll write it with f of t. Okay, so we'll put f of t equals, and it's going to be e to the sigma t, and it'll be the inverse transform of our sigma plus j omega. Okay, so now what we'll do is we'll write that out as the full Fourier transform, the inverse transform. Okay, so we're going to have our f of t is going to equal, well, the inverse transform is going to be 1 upon 2 pi, the integral of, now I'll leave out the limits of the integration for, in fact I'll just leave them in at the moment as minus infinity to plus infinity, and that's going to be, what's going to be e to the j omega t. Okay, and we're also multiplying it by e to the sigma t, okay, by our d omega, and it's going to be now our function of sigma plus j omega. Okay, so this here is just a inverse Laplace transform of the function above. So what we can do is we can say that if we let our value s equal our sigma plus j omega, then we could say that ds is going to equal, well, sigma is just a constant, okay, so it's going to be equal j d omega. So we can write d omega out again as ds upon j. Okay, so we'll put these back into this formula here. So we can say f of t equals 1 upon 2 pi. Okay, now I'll leave the limits of the integral out for the moment. So it's going to be f of s times, well, now we've got our e to the j omega t, e to the minus sigma t, so that's equivalent to writing our e to the j or e to the sigma plus j omega t. Okay, so that's the same as saying e to the value of our sigma plus j omega t. Okay, by now our value here ds, okay, our d omega is replaced by ds upon j. Okay, so we can bring the j out here and we can just put our ds there. Okay, and we know that our sigma plus j omega is just our value of s, so this thing here can be replaced by our s, so we'll just pop our s in here. Okay, right, so I can take all this out, that just gets replaced by our value of s. Okay, so that's e to the st by ds. Now the limits of integration, the original limits of integration were omega is greater than minus infinity and less than infinity, but now we're no longer dealing with omega, it's sigma plus j omega. Okay, so that now gets replaced by sigma plus j omega, so that's going to be greater than our value sigma minus j infinity, and it's going to be less than a value of sigma plus j infinity. Okay, so these are our new limits of integration. So we've got our sigma minus j infinity, and we've got our sigma plus j infinity. Okay, so this here is our inverse Laplace transform equation. Okay, now this is a contour integration. Okay, now what we can do is if we pick one particular value of sigma, for example sigma naught, then we'll be integrating along this axis sigma. Okay, so you'll see that whenever we go and we'll draw it out graphically. So in order to get an understanding of it graphically, we'll think about it initially in terms of the forward transform. Okay, so in the forward transform, what we would have is we would have, I'll try to reuse this, I'll try to make it reasonably neat. Okay, so we would have some function of time. Okay, so that's some function of time, that's the time axis. The function of time is then going to be multiplied by e to the sigma naught t. Okay, so there's t again, there's e to the minus sigma naught, I should say. That's it. So that's going to be e to the minus sigma naught t. Okay, so that's just one particular value. And then when you multiply both of these together, okay, again that's a function of time, and we'll get this function, but it will be modulated slightly. So it will come up along, it'll be 0, it will come up, and it will come down like that, and it will cut off. Okay, so this function here is going to be our f of t e to the minus sigma naught t. Now I'll try and draw this out. I'll just draw it out as a kind of heuristically. So we know we're going to take that and we're going to multiply it by our e to the minus j omega t for the forward transform. Okay, so we know that split into our cos omega t surface and our minus j sine omega t surface. Okay, so this comes in and it modulates this function, also modulates that function there. So, and then what we're going to do is we're going to integrate the whole thing up with respect to time. So we're integrating that one with respect to time and that one with respect to time, and we'll end up with this one will provide a real part, okay, of one part of our complex frequency surface. Okay, so that'll become apparent. I'll just draw these out first. Okay, so this here is going to be our j omega axis. J omega axis. This is our sigma axis. Sigma axis. This particular value is sigma naught. Okay, so along that line there is sigma naught. So that's the line that we will be integrating along whenever we do the inverse transform. So this will provide us with some function here. So let's say it looks something like that. Okay, now these aren't actual functions, I've just drawn out just heuristically, just to show you what's happening. So we've got a real part, and then we'll end up with the same here, but it'll be an imaginary part. Okay, so when you think about these as that's in that plane, and this is on a plane at 90 degrees. Okay, so that's going to be a real part, and that's going to be an imaginary part. Okay, so it means that whenever we create the overall surface for the Laplace transform, we're going to have our sigma and we're going to have our j omega, and whenever we find the magnitude of the functions at this value sigma naught, okay, it'll give some part. Okay, it'll just give one part of our f of s surface. Okay, so that's fs, the magnitude of f of s, where s is sigma plus j omega. So that's what the forward transform looked like. Okay, now our contention is that we can reconstitute this function f of t by working backwards. Okay, so working backwards through here. Now what I'll do is I won't redraw, in fact maybe I will, maybe I can just, yeah, maybe just redraw this out again just down below. Okay, so that's the Laplace transform, so I'll just put in LT, Laplace transform. Now in order to generate the inverse transform, our contention is from the maths here, what we're saying is we can reconstitute this f of t from the f of s surface by just picking one value of sigma. Okay, any value of sigma will do, and then running through this integration from the frequency minus infinity to plus infinity. Okay, and that's our contention whenever we do this here. Okay, so let's get this right here. J infinity plus j infinity. Okay, so that's our contention here. So let's just draw this out again. So what we're going to do is we're going to pick, in fact I'll just do it here with this because it saves all this redrawing this out again. So what we're going to do is we're starting from the Fourier, from the Laplace surface. We've picked one particular value of sigma, okay, sigma naught, right, and we've split that value sigma naught into the real and imaginary components. So we've got these real and imaginary components of this particular value of sigma naught. Now what we're going to do is we're going to allow the sigma naught to modulate the cos omega t surface, as opposed to the function here modulating it, the sigma naught value. So this function here will modulate this surface, and this function here will modulate this surface, and then we're going to work back this way. So I'll just get rid of some of this here, because we're going to come back this way. Okay, and I'll get rid of that as well. Okay, so whenever we modulate that surface, we then are doing the integration, but we're integrating here now in this direction here with respect to our omega. Okay, so whenever we integrate this in this direction here, we'll get one function here. Okay, so let's just draw something out, just anything, doesn't really matter. We'll call that f1. Okay, so we've got f1 by modulating this surface with this function and then integrate with respect to omega. Now we do the exact same thing with this function here, modulating this surface here, and we'll get another value here. We'll call it f2. Okay, so let's say f2 is just some function like that. Okay, and that's f2. Now what we're going to do is we add up f1 and f2, so we get a third function here, which is just, I'll just draw something, doesn't matter what it looks like. So it's some function f1 plus f2, and then what we're going to do is we're going to modulate that by, now it's going to be e to the sigma t as opposed to e to the minus sigma t. Okay, so e to minus sigma t, sit like that, so it's going to sit, you know, something along like that. Okay, so now we have this here modulating this function here, and when we come back here, we come back, and if we multiply these two together, we'll come back to the original function f of t. Okay, so that there is the inverse transform, and I think you can see graphically how it works. And again, we could pick any part of the surface and any line there with our value sigma, and then we can regenerate this function of t from that. Okay, so that's all there is to this. Hope you enjoyed the video, and I'll see you later.